Okay, hi everybody. Oh. My name is Dmitry, and I'm a software developer in a small infra group called Metasite Republic. And here you may see one of the many pictures how I try to summon my unconsciousness, subconsciousness to solve all our hard engineering problems. And today we're going to talk about memory management in JVM. What is memory management? First thing that comes to mind is we need to allocate some memory in our applications. The next thing, we need somehow to free the memory that we allocated. Otherwise, our application will run out of memory fairly quickly. Next thing, we need to be able to monitor the state of our application with regards to memory usage. And of course, we need to be able to configure our application. And instead of agenda today, here are some questions that may or may not be answered during this presentation. How and what to monitor, how to choose garbage collector, what is the optimal memory usage, how and can we limit the memory consumption of JVM, and why should we even care about memory? Let's start from the last question. When should we care about memory? The obvious answer is if we encounter any kind of out of memory, we probably should care to guess what's going on. If our application experiences general overall slowness because of the GC post time, obviously we also need to care about this. In real world, memory usually costs money, and therefore we need to care about memory with this regard. We use less, we pay less, allegedly. And sometimes we also care about performance, and if you manage memory properly, you may have some gains in performance. Okay, let's quickly iterate that we all know how to allocate memory in JVM. So we have new operator to allocate memory on heap. We have direct memory that we allocate via byte buffer. We have notoriously known class unsafe that also allows you to allocate off-heap memory. And also we have native allocations. How to free memory? In Java, we don't have delete operator. Instead of that, we have garbage collector that takes care of that. Direct memory also is taken care by garbage collector. If you allocate with unsafe, then you need to free memory with unsafe as well. And if you allocate memory in native code, obviously you need to do it in native code as well, to free memory in native code. There is system.gc, but you shouldn't probably use it, and there are very few examples when you actually need this. Okay, let's start diving into overall memory usage of JVM. Let's start with memory pools. JMX provides us with a list of memory pools and corresponding metrics. Let's see what we have here. We have 8 pools, 5 of non-heap and 3 heap memory pools. Let's focus on off-heap for now. So the code heap memory is split into 3 areas. In short, it is a cache for JIT compiler. It caches like all the compiled, interpreted methods, whatever JIT compiler needs. Metaspace, if heap is small, less than 32 gigabytes, then it is split into 2. One is compressed class files, and the rest is in metaspace. In short, metaspace is for loaded class files. all the classes, methods, fields, annotations, whatever there is, some internal representation. How much memory actually it takes for those off-heap pools? So I plotted here the graph. This is the maximum for each heap space. Approximately 400 megabytes for metaspace and 200 megabytes for JIT compiler. We don't collect, at Wix, we don't collect these metrics for all services, but pretty big services report this, so those numbers are the ballpark, more or less. What we do report is the metric that is called non-heap memory usage, and it's basically a sum of all non-heap memory pools. It is actually a good idea to report not only some, but also separately, because that way you will be able to know if you have some unusual behavior in one of the pools. Next, let's talk about buffer pools. We have only 3 of them: direct, mapped, and mapped NVM. The direct pool can be limited with this option, max direct memory size. If it's not specified, then it is equal to XMX for whatever reason. And direct memory you can allocate with byte buffer. We don't use mapped files, and mapped NVM, it's very specific to hardware. You need to use like special libraries for that. Okay, the next part of JVM that uses memory is thread. In JVM, we can create threads. Each thread needs some memory for its stack. It's not only what is allocated for thread, but this is the biggest part. We can configure it with the option XSS. By default, it's 1 megabyte. Minimum is platform dependent. On my laptop, it's 136 kilobytes. The important part is that this memory is not allocated immediately. Like when you create a thread, you don't allocate 1 megabyte of data. Operating system knows how to allocate it lazily, and I even created a small example how to show how to estimate how much memory threads actually take. So this is the simple code. Like this is the recursive function that goes to specific depth. And with this cycle, with this loop, you can actually determine what is the, when you get Stack Overflow exception, you know that this is the limit for specific configuration. And if we will implement some kind of weight before, like here, before we go into the depth, and then here when we actually reached the depth, so we will be able to actually see how much memory we allocate for the thread before and how much after. For that, you need to enable native memory tracking with the command line option. And if we call it like at this weight points, so you may see that here, like before we have 800 kilobytes allocated for threads, and after, like when we reached the depth of the thread, we can see that it's 900 kilobytes more. So like eventually it allocates more and more memory. And this thing, native memory tracking, it's a very useful tool for debugging. It can provide even more information, but sadly it's in plain text format. Okay, now let's talk about the most important bit, which is garbage collector and memory related to garbage collectors. First, we have memory pools. Now let's focus on heap memory pools. And we can see that for G1 GC, we have three memory pools: Eden space, survivor space, and old generation. In general, most of the garbage collector, they use this idea that you need to split memory into young generation and old generation, and mostly you allocate objects in young generation, they quickly die, and so you don't need to touch during garbage collection the old generation. This is a very simplified view because each GC algorithm actually uses this theory, but the implementation details might be wildly different. So what do we have? We report a single we report more metrics, but basically we report metric heap memory used, which is the sum of all these memory pools that related to heap memory, which is obviously not always good because we don't have further introspection into all the memory areas of garbage collector. Our metrics are collected once a minute. This is our default sampling, and which means that when we report this metric, get heap memory usage, we get some arbitrary data point within a minute. We may ask why, because obviously a single data point within a whole minute, it's probably not very useful, especially for debugging, but this is how it was for a long time. Not so long ago, we introduced another metric that is sampled once in a minute, once a second, and we report the maximum within a minute, sampled every second. I claim that this is still not very good, but it's much better than like single arbitrary point. Instead of that, now we have one of the 60 data points. Okay, let's see what memory pool MXBin provides, which data we can get from it. So get usage, this is actually what this is the usage, current usage of the memory pool. Get collection usage returns usage of the memory after the last garbage collection, which is not very useful because, for example, for young generation, it will usually return 0 because usually we empty entire young generation. And also we have peak usage. Get peak usage actually returns the maximum throughout the lifetime of the JVM. It is calculated by JVM itself. So whenever JVM collects the garbage, it gets the current usage and chooses the max. It's very nice, but the problem is that garbage collector, the size of young generation, old generation are not constant. Like garbage collector is its own right to actually dynamically change the sizes of these areas. And in production, because of that, we can have sum of peak of young generation and old generation to be more than XMX. So this is the problem. We can mitigate this problem by resetting this value once in a while, and therefore we will get true maximum, not sampled maximum, but true maximum within some time frame. We can reset it like once in 10 minutes, for example, or like once in 5 minutes. And it's actually precise instead of being some more or less random. Another cool feature of JVM is GC logs. not only GC, but we are going to talk mostly about GC now. So GC logs, actually, they have all necessary information to know about garbage collector, why it was run, how much memory was freed, and so on, and how much time it took. The problem with GC logs that they are unstructured, so therefore it's hard to parse, hard-ish. Of course, it's possible to parse, and there are parsers for GC logs. The fun fact that currently, like this is our configuration of GC logs, how we log it. And the problem here that we use blocking writes, not async. And there is an option to make it async. And I have a guess that we had the incident in production that one pod had huge GC post time. We take a look at the server and we saw that like IOPS went through the roof, and probably because of that, when we tried to write to logs, it just waited in queue for a long time, and this is why we had a very unresponsive application during that time. So I think we should do better and enable asynchronous logging. So the problem of GC logs that it's unstructured, and it's harder to collect those logs and do any kind of analysis. But inside JVM and JMX, we actually have possibility to receive almost the same data via notifications. So we can add our custom listener for garbage collection, and after each garbage collection, we will receive callback. There are plenty of details on this slide, so let's go over all the parts. So first, we have a list of garbage collector bins. There are more than one garbage collectors because for each algorithm it's different. For example, for G1 GC, we have 3 garbage collectors, and they run at one time. Only one of them is running, so they do different job. For example, G1 young generation collector never touches old generation at all. For parallel GC, ZGC, and Shenandoah GC, there are 2 collectors, and for generational ZGC, there are 4 collectors. Nevertheless, like this way, we can distinguish between different garbage collectors types, what they do, and report separate metrics. So we receive this data for each garbage collector. So the action, the cause, what caused this garbage collection, and the most important, we get start end time and usage before and usage after. This map basically contains memory pools of garbage collector that we talked about before. So by subscribing by adding this listener, we can actually report separate metrics for different kinds of garbage collectors, and we can report interesting metrics like the diff from before and after. And also, if we store, for example, end time of the previous garbage collector, then once we receive the next notification, we can actually calculate how much time it took passed between current garbage collector and previous one. So duration, we can calculate duration between garbage collections, which might be useful. Okay, which one garbage collector we should choose? There are plenty of algorithms, and like some of them we shouldn't use ever. So serial GC is completely sequential, single-threaded, stop-the-world garbage collector. Obviously, we don't want to encounter sometimes large pauses. Parallel GC is one of the oldest garbage collectors, allegedly with the best throughput ratio. Concurrent mark and sweep was removed in JDK 14. Current default is G1 GC. And there are Shenandoah GC and ZGC. Both garbage collectors are aimed to support very big heaps and to have as low GC poses as possible. And another fun garbage collector called Epsilon GC. It's basically no op, meaning that there is no garbage collection. It allocates memory until it's full, and after that, application will always receive out-of-memory error. Maybe for some usages, for like testing and short-lived applications, it might be useful. At Wix, we historically used CMS long time ago, and then when we switched to JDK 11, we switched default to G1 GC. So what are the criteria how we choose garbage collector? We have two main metrics for two main characteristics of garbage collector: latency and throughput. Latency is how much poses your application suffer from garbage collector, and throughput is how much CPU resources GC uses against how much CPU is left to your application. I borrowed this very simple flow chart from gceasy.io. They are very famous for their GC log analyzer. And basically, in order to choose garbage collector, we need to answer three questions. Is our heap small, meaning that less than 32 gigabytes? Do we care about long pauses? Long in that aspect means like 3 to 30, 50 milliseconds. It's not like seconds. And do we care about high throughput, meaning is our service heavily loaded? At Wix, majority of services are stateless gRPC services. So what we can actually answer all these questions like for 98, 99% of all Wix services. That we don't need a large heap. We don't care about GC pause time too much because the pauses are short. So we rarely see any effect on response time because of the GC pauses. And we want to have high throughput, meaning that we want GC to work less and most of the CPU resources to be given to our application to do the work. And based on this flow chart, we can say that our default choice should be parallel GC, but our default is G1 GC. I will cover this topic a little bit later. So another aspect of each GC algorithm is overhead. Overhead means that GC by itself needs some memory to operate properly. So for example, serial GC almost don't need, like, it doesn't need too much memory because like it's fully sequential. But for other GCs, it might reach 10–15% for G1 GC. So like if you have heap of, I don't know, 4 gigabytes, it means that about at least 400 megabytes will be taken not from the XMX, a side of XMX will be taken by GC itself. But it's also heavily dependent on actual load profile, how application is using memory. So it's hard to tell how much exactly. There is a way to know how much memory GC actually takes, but for that you need to enable native memory tracking, and it's not free. Native memory tracker itself, it takes CPU, and also it takes extra memory for each allocated object in order to track it. So it's probably not a good idea to run it in production, but if you're debugging stuff, this is the way to go. Yeah. Okay, how do we limit the memory usage in JVM? Let's reiterate what we have in JVM. We have code cache. There are options to control code cache. There is metaspace. We have options to control the size of metaspace. By the way, by default, metaspace is unbound. It can take whatever. We have XMX, obviously. We have GC garbage collector memory footprint that we cannot control at all. We can only look how much memory it takes. For threads, we have XSS option. Direct memory is controlled by the option, but also we have native allocations, we have unsafe class, and other stuff that is provided by operating system. For example, if you open connection, operating system will also allocate some memory for internal buffers and so on and so forth. So, so TLDR, you cannot limit memory usage of JVM at all. So there is no way of protecting our application from being killed by out-of-memory killer. And this we need to keep in mind. Basically, we need to hope that our configuration is good enough to not be killed, but there is no guarantee at all. Okay, the next big question is how we actually can determine the size of the heap, how we can configure XMX. In general, don't read entire thing. In general, in internet, you can find some advices how to do it, but they are all very vague. And basically, they say you need to have enough memory for your application, and sometimes as much as possible memory for your application. And also, you need to monitor performance metrics to know if it's good enough or not. So let's come up with something more concrete. But I must warn you that it won't be as concrete as we all actually want to be. So the way to find the optimal XMX for your application is to do load tests, which is cumbersome, of course, but what can you do? Either you go YOLO with some default and hope for the best, or what we can do, we can plan ahead, so we can measure how much in-memory caches do we have, what are the sizes, so we can understand how many bytes we need in old generation, more or less, and then the best thing to know is how much memory you need per request. But since we usually we don't know, and it's very hard to know, because I don't know, one site is one small site with a single title, another site is with 200 pages, so the sizes of objects are different, so you cannot actually know how much memory you need per request. So instead of that, we guesstimate the size of the instance in terms of how many CPUs we might need for our application based on, I don't know, expected throughput of this service and how many instances we want to have in our cluster and so on. Then we need to choose some GC algorithm, maybe based on the flowchart. Then we need to choose some XMX and then perform load test and then check metrics, again, something, adjust memory and repeat load test. So basically we need to go into this loop. Configure, perform load test, analyze metrics. What metrics actually we need to check? It's very unclear actually which ones. So again, we have some metrics here, like I stated a few metrics here. CPU utilization is a metric that you need to check in your load test to be in correspondence with the auto-scaling target, basically. It doesn't make sense to do load test in which you will consume more CPU or less CPU than your actual target in production. So your load test should show you how your application operates normally under normal circumstances. Obviously, you need to check response time and GC post time. It's actually very hard to tell what you need, how it can help you, except for the fact that if you change XMX and GC post time grows, then it's indicative that at some point there will be a problem. All the metrics that are marked with asterisks, we don't report those metrics yet. Hopefully we will start at some point. But some of these metrics might be helpful. In what sense? So duration between GCs, as I explained before, it is how much time happens between two garbage collections. By itself, again, this metric is very unclear how to use it. But once we start measuring it and doing load test, what we will see is that if you have a lot of memory, much more memory than you need, then the duration between two consecutive garbage collections will be long, like seconds, even minutes sometimes. So if you see this behavior, obviously you know that you have too much memory, so you can reduce it. And then reduce until what point? And this is very hard to tell actually, because for some applications in production that I tested, the good value would be 2 seconds between garbage collections, because I have a larger heap for these applications, and for smaller heaps, it can reach even half a second. So every half a second there is young generation garbage collection. So it comes with some experience in load testing. And now it is time for a story. So once upon a time, we decided to check, okay, we use by default G1 GC. Should we use another GC? It was almost a year ago. Back then we used OpenJDK 17, and it didn't include Shenandoah GC. So we checked only parallel GC, G1 GC, and ZGC. And ZGC in JDK 17 is not generational, so it has single heap. So first we decided to check ZGC because the promise of zero post time. We enabled it for the service, and then throughput per pod dropped 2 times immediately. We thought about it, what can we do? We increased XMX 2 times, and then throughput per pod returned to the baseline. Also, it consumed more CPU, with 2 gigabytes. So the GC post time almost went to 0, indeed. But we didn't see any improvement in response time. Arguably, it was maybe 1 millisecond for median response time. For maximum and higher percentiles, you cannot say that there is any difference. So basically, we looked at this. It consumes more resources. It doesn't provide any benefits, so probably not good for our specific use case. Then we switched to parallel GC, and there was immediate success. So here you can see that we turned on parallel GC, and after autoscaler downscaled our cluster, we saw like 10 to 20% increase in throughput per pod, therefore like 10 to 20% less instances of the service. With regards to GC post time, you can see that it actually increased GC post time. But when we checked response time, we actually didn't see any difference. So the median, higher percentiles were the same as with G1 GC. For most of the services, highly loaded services, we had more or less the same kind of improvement, like 10 to 20% in throughput. But for the services that do mostly I/O, they proxy a lot of bytes here and there were no changes at all. Like one GC, another GC, all the same. Success, right? But we thought about, let's push parallel GC to everyone. But we found one service, old legacy bootstrap service, that after changing it from G1 GC to parallel GC, it improved a little bit, and then it hit another bottleneck somewhere in JT threads. So we couldn't enable parallel GC for that service, so we decided not to pursue switch of default garbage collector, since G1 GC just worked. And this is where my personal story actually begins. So while I was preparing for the conference, I wrote reporting of many more metrics, like duration between GCs and everything else. So I decided, wow, let's just do the same experiment and see also not only like the throughput per pod, which is amazing, but let's see how other metrics are different. So I switched back from parallel GC to G1 GC, and there were no changes at all. And this was like a couple weeks ago. So to be truthful for my audience, obviously I decided, okay, I need to understand what's going on. I don't want to tell you a story of almost 1 year ago, how we improved everything. It took a lot of thinking, and then I realized we actually switched to another JVM. So we went from OpenJDK 17 to Graal VM of JDK 21. And then I went to changelog, and I found multiple improvements for G1 GC. They reduced memory footprint of G1 GC, they improved performance. There was some improvements for parallel GC as well, but basically there were a lot of improvements between those versions. Okay, so what I need to do? I need to do load testing again. I wrote a script that automates load testing, changes GC algorithm, changes XMX, and all of that stuff. I waited for many hours for it to complete, and then I started to analyze it. So this is the response times for parallel GC. Let's focus on median only, like it's about 10 milliseconds. And then G1 GC, and we see that it's slightly higher, it's like 12 milliseconds, but it's very close. And then, sorry, can we make a full screen? So we, the baseline for the service was 2 gigabytes of XMX. So I decided, okay, let's check how they behave by lowering XMX more and more and more. Let's check how it goes. And what I discovered is that basically we went from 2 gigabytes down to 1.2 gigabytes, and after that parallel GC stopped operating completely, even like in half throughput, like it just died basically. And it's not this. Sorry, this. And those are the numbers. So basically, response time is slightly higher in G1GC. The pause time is also higher in G1GC, but slightly higher, not like 10-20% of benefit. We actually saw like maybe 1-2%, which we cannot actually see on regular graphs in production. The one benefit of G1GC that it continued to operate once we reduced XMX down to 800 megabytes, which is actually crazy. And it actually held the same throughput. Granted that it consumed much more CPU than on a regular level. So TLDR parallel GC is still better, but slightly better. So I have all the time. I want to leave you with just one thing more. This is the prayer for garbage collectors. God grant me space to accommodate what I still need, the courage to remove what is no longer useful, and the wisdom to distinguish one from another. I actually it's not mine. During the preparation, I just encountered this on a Russian blog post, and I translated it. For me, it's hilarious. Thank you very much.